Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good morning, I'm Kenny Guro from the Embedded and Reconfigurable Computing Group here in Research Redmond, and today it's my pleasure to introduce Russ Tessier. So Russ Tessier is an associate professor in electrical computer engineering at University of Massachusetts Amherst. He received his SM and Ph.D. degrees in electrical and computer science from MIT in 1992 and 1999 respectively. Russ has worked professionally at Altera and Mentor Graphics, among other companies. His interests include reconfigurable computing, embedded systems, and multi-core processing. So please help me welcome him.
Thank you, Ken. Today I'm going to talk about network virtualization using FPGAs. My background is primarily in the FPGA area, but about 3 or 4 years ago, I started to get interested in networking, and I started working with a faculty member, Lishan Gao, who's an expert in networking. And we decided to start exploring sort of a new trend in networking, the idea of using hardware, routing hardware, to serve different routing purposes at different times. So the same physical hardware that can change its functionality over time to provide different network functionality. So today I'm going to talk about how this goal can be achieved using field programmable gate arrays. Okay, so before I start, I'd like to also acknowledge my colleagues. Most of the work I'm going to talk about today is the PhD work of my student Deepak Unnikrishnan, another PhD student Dong Yin, and Professor Lishan Gao from UMass. So I'm going to start off today with an overview of what network virtualization is. It's a topic area that's gotten a lot of attention in the last 3 or 4 years. People have looked at different ways of making the internet and networking in general more functional. Okay, being able to reuse the same hardware over and over for different purposes, and in some cases using the same hardware for different routing purposes at the same time. Okay, so I'll give some examples today and show how this can be done in hardware and also in software. One of the challenges of the FPGA community over the years is identifying application areas that take advantage of the reconfigurability of FPGAs. Okay, and it turns out that this application I'm going to talk about today is particularly good for dynamic reconfiguration of the FPGA field programmable gate array device. So I'll show that for the work that we did today, we used both complete device reconfiguration and partial reconfiguration at runtime in order to be able to serve some of our needs in virtual networking. I'll describe a complete FPGA-based virtualization system that allows us to be able to route packets at line rate for 1 gigabit per second Ethernet. We're working on a faster technology currently. And then finally, I'll finish off with a discussion of how we went about making this particular implementation partially reconfigurable, and I'll finish off with some results. I'd also like to encourage everyone, if there are questions or comments that you'd like to make in the course of the talk. Of course, I'm used to giving lectures to students with lots of questions or clarifications. So feel free as I talk to ask questions if there are things that aren't clear. Okay, virtual networking. Over the history of networking, for the most part, the network routing hardware, the hardware that physically transmits the packet, have been fairly static, fairly fixed function. Okay, but as time progresses, there's a need for more diversity in the network. Okay, we've seen sort of an explosion of cloud computing, data centers, a variety of other sorts of applications, and a variety of needs that present different bandwidth requirements, different security requirements, different isolation requirements at different times. Okay, so it's desirable to have a system that can provide different functionalities, different sort of qualities of service at different times without having to completely replace the hardware, without having to come up with completely new protocols that can be implemented at the system level. For the most part, over the last 3 or 4 years, there's been an explosion of this interest in the idea of virtual networking, taking a physical piece of hardware, routing hardware, and changing it over time to be able to serve different functionalities. It doesn't even necessarily need to be the hardware. It also could be the software which is being used to route packets in a system. And in fact, the system that I'm going to talk about today includes both hardware and software as a platform in order to be able to route packets. We also view this as an opportunity for service providers to be able to make an investment in an infrastructure for networking and then go about changing and adapting the system over time. We think that that can be an effective business model as people create different needs and different applications and different protocols that can be implemented on the hardware. Okay? So the solution to all of these issues, as I mentioned, is network virtualization. Reusing the same hardware for different purposes at different times. The key question is, how can we go about providing the same quality of service, the same throughput, the same security, and the same isolation for systems by using the same hardware, or potentially using the same hardware from multiple networks at the same time without having them collide with each other. Okay, so the goal of this research is to investigate some of these issues. Another issue that we're evaluating in this research is one of scalability. Okay, how can I implement a large number of network routers, a large number of network data planes on the same physical hardware and timeshare that hardware in a way that's similar to the use of a microprocessor and its use across a variety of different applications on a standard PC. Okay, so I'll talk about some of the techniques that we're using in order to be able to do that today. So network virtualization, we can think of a virtual network as a collection of nodes. Okay, so I have a picture here of two virtual networks, a blue network and a red network. And we can see here that some of the names of these nodes overlap, and the topologies of these two networks are dramatically different. Okay, one is more of a point-to-point type connection between different nodes, and others have this other network has a little bit more connectivity. But roughly, in terms of performing the connectivity, it's possible to see that, in fact, both of these networks could be generated using the same hardware and the same physical links. So, for example, if I had a situation with a series of computers, which are located down here, and a series of routers represented by these boxes here, if I could come up with some way of sharing the resources, the routing resources, programming the resources in a way that forwards packets in a predictable or in an application-specific way, it's possible to be able to implement this system effectively. Now, about 3 or 4 years ago, most folks looked at this and implemented this type of system using software. Okay? And I will talk about a software system that was developed at my school based on something called OpenVZ, which allows for kernel-level forwarding of packets in providing virtualization. When we looked at this 3 or 4 years ago, a decision was made that, in fact, software is too slow for this type of application. So it's desirable to put some hardware in the system, but continue to allow it to be scalable. Okay? Allow it to handle not just one, not just two different virtual networks, but to allow it to handle a large number of virtual networks. In effect, almost close to an infinite number of virtual networks, as long as the various constraints of the networks were met. Okay? Developing a system like this has a lot of benefits, obviously. There's the goal of reducing costs. It's not necessary to make investments in a large amount of routing hardware, since the same hardware can be used for multiple networks at the same time. Additionally, as protocols change or as techniques change, it's possible to update them to allow them to be able to be used simultaneously in an independent fashion. Okay. So when I say virtual router, what do I mean? Well, I'm going to use the term virtual router in this talk, although perhaps a more accurate term would be virtual data plane. Okay, so the virtual router is really split into two parts. There's a control plane, which defines how the packets are forwarded, and then there's the data plane, where the actual physical hardware determines where an incoming packet is sent to. The focus of this talk really is on the data plane, although I do use the word virtual router quite a bit in this particular talk. We can get this idea of a physical router which is being time multiplexed across multiple different virtual routers. So, for example, in this case, the physical router has two physical interfaces, one for input, one for output, but the core hardware, processor, FPGA, ASIC is being time multiplexed at different times to perform different functionality. So, for example, in this case, for the example I had on the previous slide, there were two networks. I might, for example, have two sets of hardware which are performing the routing for the two different networks. And the key parts of the router include some routing control, and then also the forwarding table, the data plane, which actually determines when a packet arrives, where it's sent to as a destination. Okay? In this particular picture, I show two virtual networks. It's common in if this was implemented in software, it's common to have 10, 15, 20, or more virtual networks. In the FPGA work I'm going to talk about today, we were successful in implementing up to 5 virtual networks in a relatively small FPGA. In a much larger Vertex 5 FPGA, it was possible to implement up to 30 different virtual networks. Okay? So some of the challenges in implementing this, whether it's in hardware or software, is making sure that there's sufficient resources in whatever the deployment device is for this particular technology. So for example, in the FPGA, the obvious constraint is the amount of hardware that's available. If I run out of space in the forwarding table, if I run out of space in the logic, I can't implement more virtual networks. There's also an issue in terms of performance. I want to make sure that I can meet the constraints for all the networks at the same time. Okay? If the hardware is being multiplexed, there's this idea of flexibility and also an idea of scalability, being able to change the network over time. Okay? The place where the FPGA comes in this particular example is that over time, the different virtual networks will change. Okay? Some new virtual networks will be formed. Other virtual networks will be taken away. Okay? The FPGA provides the capability to be able to modify the physical hardware at different times to accommodate new virtual networks as they're created or as they're destroyed. And we've developed a system that has the capability to do that. Okay, so some of the traditional techniques that go about doing this, there have been a large variety of papers. Yeah, question?
Can I ask a question on the previous slide?
Yep.
Is there a one-to-one mapping between the number of virtual networks that you want to support and number of virtual routers?
For this particular work, there is. We have not looked at cases where there were a different number of virtual networks and a number of virtual routers. One could think of techniques where you could potentially have networks which had, an individual network which had different parameters at different times, so there wouldn't necessarily be a one-to-one mapping. But
why can't you, for example, let's say you have virtual network A and B and one router, why can't the packets from one of these networks, why can't just the packets be different? Like the header says, this is the packet from network A, and then you have one router that, you can treat the packets from this network, with higher quality of service or whatever parameter that you want to set. Why do we need 2 separate, copies of the hardware?
So that's a good question. I think for this picture, I sort of provided a logical viewpoint. And in fact, in the actual hardware that we implement, a lot of the hardware is actually shared across the different networks. So for example, in this case, they would have separate forwarding. I show here separate forwarding tables, but in fact, the forwarding tables are implemented in the same physical memory. And then it's just a matter of indexing into the appropriate place. Okay, so most of the techniques that have been developed to implement virtual networking have been in software, both kernel mode and user mode forwarding for packets. I will show a little bit later in the talk that in fact this is orders of magnitude slower than what an FPGA can do in terms of being able to forward the packets. There have been other works in FPGAs recently since we started our work, but in general most of the techniques involve either software or an ASIC approach. In general, for obvious reasons, the software is limited both in terms of parallelism and in terms of some functionality due to hardware limitations. But it is obviously very flexible, so it's possible to implement a large number of virtual networks in software for the system. Another technique which has sort of become less popular over the last 4 or 5 years is to develop ASICs, which have these separate networks implemented with some sharing. Sort of the classic example of this is the supercharging Planet Lab platform. There's a few other ones as well. Of course, an ASIC starts running into the same problems we had with fixed networks, and they can't be modified over time, and they have some limitations associated with them. Okay, so what are the 3 good reasons why FPGAs are such a good platform for implementing virtual networks? Like a lot of applications, FPGAs have specialization. Okay, they have the capability to implement exactly the network that's necessary, or the network hardware that's needed in the FPGA hardware, which provides a lot of benefit. Okay, A second reason is that the FPGA doesn't have to be by itself. Okay? The fact we include an FPGA in the system doesn't mean that the FPGA has to be the only thing that's performing the packet routing. And in fact, the word scalable in my talk here means that there are virtual networks in both the hardware inside the FPGA and also in software, which is being implemented on an accompanying workstation. Okay? One of the goals of the work is to allocate the high-speed networks, the critical networks, to the FPGA, and to allocate the lower speed or lower quality networks to the software, and to dynamically change the allocation over time as necessary. And the third reason why FPGAs are desirable is because they provide the capability to do dynamic reconfiguration. A portion of the FPGA continues to run in forward packets while a small portion of the FPGA is changed. Now, that's not universally true for all FPGAs. Up until recently, Altera had FPGAs which you couldn't do that. But in general, for a lot of the higher-end FPGAs, it is possible to do partial reconfiguration. As a member of the FPGA community, over the years, folks have had lots of tools and ideas for partial reconfiguration. Sort of the application space of where partial reconfiguration is useful has been somewhat, the more classic examples you see in the literature are encryption, where a key is changed, or a filter, where a parameter is changed, or some other things. This particular application does really benefit from partial reconfiguration in a large scale, not just a small one for a few parameters. Okay, so let me talk a little bit about our platform now to give you a sense of what this overall system looks like. We implemented our virtual networking system using a NetFPGA board from Stanford. It's a NetFPGA 1G board. In fairness, this system is old. Okay, it's about 6-7 years old. My group is currently migrating, or has migrated, the technology to a newer board from Altera, which I'll say a few words about at the end of the presentation. But most of this talk is going to focus on this NetFPGA product. The NetFPGA is a board which plugs into a standard PC. You can buy a cube off the shelf from a company that has all the appropriate software installed. And the idea here is that we would have a Linux-based PC which has a series of software virtual routers which are being implemented in kernel mode. And there's also accompanying through a PCI interface a NetFPGA board which has a series of hardware virtual routers implemented inside this rather small Vertex 2 FPGA. And the idea would be to be able to swap the configurations as necessary. If one of the virtual networks is no longer needed, one of the routers can be kicked out of the FPGA, a new one can be put in. If it turns out there's room in the FPGA, it's possible to migrate one of the networks from software into the hardware. There's a total of 4 ports here on the 1G Ethernet interface, and by today's standards, a relatively small amount of SDRAM and SRAM that's part of the system. Okay, so I'm going to talk about 2 techniques. Yeah, sorry.
So the network that's getting implemented is coming through the 1G on the NetFPGA, or is it the NICs going to the Linux host?
Okay, so good question. The answer to that is yes. So there's 2 different modes. There's one called single receiver mode and one called multi-receiver mode, which I'll talk about in just a second. Okay, so basically you can do it either way, depending on how you want to do the reconfiguration. Okay. So just a higher level block diagram of what's happening here. We can see that here's the physical interfaces over here for the input, physical interfaces for the output. You'll notice that the physical interfaces not only have physical MAC coming in from the outside, they also have a way of transmitting information over the PCI bus from the software into these queues which are located in the NetFPGA. As I'll mention in just a second, there are actually 2 different modes we can run. One where all information is received at the NetFPGA card and then is parceled out to the appropriate place. Another technique where a switch is used to be able to split up the traffic and be able to transfer the data dynamically. It turns out that the choice that is used for how the data is split up depends on what sort of reconfiguration mode that you want to use for the FPGA. Okay, so again, I just sort of mentioned this. When we started this, the goal was to route everything through the NetFPGA hardware. Okay, and there are some real limitations to be able to do that. Initially, when we started the project, we didn't use partial reconfiguration. We used a reconfiguration which involved modifying the entire FPGA, okay, which makes it very difficult to be able to use just one single location where packets are being received. So we moved to a technique, at least initially, called the multi-receiver approach. So I'm going to start off with a discussion of the multi-receiver approach first and describe some of the challenges involved in that. And then I will move on to the technique, the more advanced technique, which we used later in the project, which involved having all the packets arrive at the net FPGA board. Okay, so one of the goals of this work was to try to figure out how can we receive information for the network, how can we for the networks, how can we allow for changes in the hardware, okay, without upsetting the traffic which was not changing. So in other words, if we implement multiple virtual routers in hardware, if we change one of them, how can we do that in such a way that the other routers are not negatively impacted and they continue operating in an efficient fashion? Okay? So as I mentioned, we tried two different approaches. The first one I'm going to talk about is the multiple receiver approach. Okay, so here's a picture of the multi-receiver approach. We can see for the multi-receiver approach here that there are switches that are located out here outside the hardware. Okay, so here's the source, here's the destination. And these switches basically make a determination in terms of whether a particular packet should be routed in the hardware, in the FPGA hardware, or they should be routed by using one of the software virtual routers. And we can see here that this looks relatively straightforward in terms of being able to implement a routing path. The router which was implemented in the net FPGA hardware was the reference router that was available from Stanford. It has an arbiter in the front here which determines as packets arrive which particular router should be handling the packets. There's a table over here which indicates the virtual IP indication in terms of being able to select the router, whether things are being implemented in hardware or software. For this particular multi-receiver approach, we're only interested in the hardware implementations, at least for on the net FPGA. And then finally, inside the virtual router, there's a lookup into the forwarding table to determine what the destination is. And then ultimately, the packet is sent out through an output queue back out to a switch to whatever the destination is, onward to the next node. A similar path is taken for software. We can see here the packets arrive over here at the PC NIC, and they go through a bridge and are effectively the same sort of process takes place. There's a lookup in a forwarding table, and the information is then sent out back to the switch. I've given this talk before, and people have asked me, well, it sounds like you're only doing modifications of the forwarding table. Why do we need all this extra hardware? In fact, we do have some, even though this talk doesn't focus on it, there are other examples that we have where other changes beyond just the forwarding table lookup is different. So in other words, it's possible to put in rate limiters on some of the traffic for some virtual networks, but not others. There's other sort of protocols. The student has implemented something called a ROFL protocol for some networks and a more standard routing procedure for other networks. So it is possible, actually, these virtual routers can have significant differences beyond just performing forwarding table lookups. For this particular talk, though, I'm focusing on the forwarding table lookups portion of this. Okay, so what happens if we use this dynamic approach? Yeah, go ahead.
How would you decide which is going to be in software and which is in hardware?
So we have a scheduling algorithm I'll talk about at the end that makes the determination based on required resources, which resources should be in the hardware and which should be in the software.
So you could route through either one for any of the networks. It's just a performance difference that you choose it?
It is a performance difference. Some networks, if they have high enough requirements, would have to go in the hardware. Okay. So for example, let's say that you worked at a data center and there was a need to route some packets. One of the users wants to create a network. If there's, if the bandwidth is where the requirements are high enough, it may be that particular network would only be suitable for the hardware. If it turns out there's too many that have to go in the hardware, then there would have to be some sort of an idea of which one would be most appropriate. Okay. So let me say a few words about what happens if we perform dynamic reconfiguration of the FPGA for this multi-receiver approach. Okay. So as I mentioned, there are multiple virtual routers implemented in the hardware. If one of the virtual routers needs to be changed in this multi-receiver approach, the first technique that we tried was to reconfigure the entire FPGA. Okay, and as a result of that, the other virtual routers which are not being changed for a short period of time are actually not functional, which would seem to be a bad thing. Okay? So a way to overcome that would be to migrate, if the entire FPGA is being modified, one way to overcome that is to migrate the functionality for the virtual routers which are not being changed to software for a period of time, reconfigure the FPGA, and then migrate those routers back to the FPGA after the new router has been put in place. Okay? So in looking at this, we can see here that the steps involved for a while, if the FPGA is being modified, moving all the networks which are not being changed to software at, granted, a much slower bandwidth rate, reconfiguring the FPGA, and then moving the networks back to hardware. So we call this a static FPGA approach. So effectively, the FPGA is shut down for a period of time. This is not the most effective approach. I'll talk about a more effective approach in a minute. But at least from the first part, in terms of studying this, it did provide a way of at least providing initial testing. I'll mention later that the total amount of time necessary to perform this reconfiguration is around 12 seconds. Okay, it doesn't take 12 seconds to reconfigure the FPGA. It does take 12 seconds to remap the ports for these networks which are being migrated from hardware to software. Okay, so after the FPGA has been reconfigured, the networks are moved back into hardware, and then the routing can continue. Okay, so after we finished the multi-receiver approach, we moved on to this idea of using a single receiver. And the idea here would be just to get rid of all the switches and all the having to reconfigure the entire FPGA every time. So the idea would be that everything, all the network traffic, is received over here at the input to the net FPGA, and then there would be hardware inside the net FPGA which would figure out if a particular packet should be routed by the FPGA hardware or by the software which is located on the PC. Okay, and this makes it a lot easier if we want to perform a dynamic reconfiguration. In this case here, if I want to go about modifying a particular router in the FPGA, and the routers have been created properly, it's possible to dynamically change only the router hardware which is affected. Okay, only the forwarding table information and the logic associated with the virtual network is modified via partial FPGA reconfiguration. Okay, so this is an example here of how a packet. Let me go back a second. This is an example of a packet that comes in from the network, is identified as being as it should be routed by software. The packet is forwarded from the net FPGA board through the PCI bus to software. A lookup takes place over here in the software virtual router, and then the packet comes back out. Now that its destination has been determined, the packet comes back out and is then sent out via the physical interface of the FPGA hardware. So another benefit of this approach is we don't need switches out in front of the board, which cuts down on some of the cost. Okay, so if we want to perform partial reconfiguration of the FPGA, we need to take some steps. Okay, and some of you I know are FPGA experts, some of you may not be. Although FPGAs provide the capability of partially reconfiguring the device, in other words, leaving a large portion of the device operational while a small portion is being changed, in general, until recently, the FPGA companies haven't spent a whole lot of time worrying about making it real easy for people to be able to do that. Fortunately, that's why we have graduate students. But it is possible to do it, although it's a little bit painful. In allowing for this single receiver approach, we had to construct the system so that most of the FPGA design, most of the reference router, is stable. Okay? Most of it does not change while the FPGA is being modified. But that small pieces of the FPGA, namely these partially reconfigurable regions, would be the part that would get modified when a particular network is being swapped out. Okay? And one of the limitations in the current FPGAs is that in order to be able to have a partially reconfigurable region, they need to be isolated from the other logic in the device through a series of bus macros. They basically have to be of the same size, same physical size, typically either a portion of a column FPGA logic, or a whole column in the case of the Vertex 2. There's a little bit of work necessary in order to be able to download the configuration. In our case, we used a JTAG interface to do the reconfiguration, the partial reconfiguration of the FPGA device. Okay, so here's kind of a snapshot of the Vertex 2. Here's a couple of macros that we made. You can see there's bus macros which isolate the partially reconfigurable region from the remainder of the logic in the chip. It turned out that in this case here, we were able to fit up to about 2 partially reconfigurable virtual routers in the Vertex 2. It's also we did the same experiment with a Vertex 5, and it was possible to implement up to 20 of them. With the larger chips, Vertex 6 and Vertex 7, you could literally implement 40, 50 of these different virtual routers in the physical hardware without too much trouble. So this device is actually on the smaller side, but it still is, unfortunately, the NetFPGA is still the one that's used by most people for networking research. Okay, so I'm going to move into talk about some results now that we generated for this project. This system was implemented in the lab. We have several NetFPGA cubes that we used to generate some of the experiments. The idea was to get an understanding of the overhead of doing this reconfiguration, of the benefits of using this approach versus the software approach, and then finally to understand the ideas regarding scalability. Okay? So as we add more virtual networks to the system, what happens? So we can see in this case here, we actually wound up using 2 boxes to perform these experiments. The NetFPGA project has a suite of tools. So they have a reference router, which will actually route packets. It's in Verilog. You can download it and run it on the board. They have a packet generator, which will generate packets at line rate and allow for experimentation with the packets. So we did some experiments here. We generated packets using the packet generator available from the NetFPGA folks, and also iPerf, which is a software packet generator, which is much simpler. And then finally, we implemented the software virtual routers using a platform called OpenVZ that was implemented in Linux on top of Linux on the PC, and measured the overall results for the system. Okay, so some of the things that we ran into is that, as I mentioned, to do the full FPGA reconfiguration, the static reconfiguration, it took about 12 seconds to basically migrate virtual networks from hardware to software, reconfigure the device, and then migrate the networks from software back to hardware again. And the reason it took so long to be able to do this was because it was necessary in the network to remap where the packets were being sent. Okay? Since there were switches in the network, it was necessary to figure out where the packet would be sent. For a short time, if we have a small number of virtual networks, it doesn't seem like that bad of an approach. But if there's a lot of virtual networks, shutting off the entire FPGA probably doesn't make a lot of sense. Okay? So there's really a strong motivation here for partial reconfiguration. The partial reconfiguration, the modification of just one of those little portions in the FPGA, only took 0.6 seconds. Okay? So it's a lot faster. And I'll show you in the results in just a minute that, in fact, the throughput, the performance that you get is substantially better than this other static approach. Okay, so first thing we looked at is how well do we do versus the software technique. If you implement these routers in software, what happens? Some of this is based on the packet size. Obviously, the bigger the packet size, the better, because you don't have to route things as information or look at the headers to figure out where the packet is going quite as often. This is a log scale, so we can see here that in general, in all cases, the FPGA-based router, the hardware virtual router, was able to operate at line rate. And this is, of course, the 1 gigabit per second Ethernet interface. In fact, there was a lot of slack associated with this. We could have done a lot better than the 1 gigabit per second based on the speed of the FPGA. And in fact, some of the faster FPGAs that are available, don't have any, with some of the experiments that have been done recently, don't have any trouble getting to 10 gigabits per second or much higher than that. This is a consistent rate, whereas the software, especially for small packets, actually did pretty bad. Okay, so we can see it's at least 2 orders of magnitude worse. Most of that is due to the overhead of being able to get the packet into the software, doing context switches, et cetera. In general, the performance was certainly not scalable or beneficial. In this case here, this was only for one virtual router. Okay, so this didn't involve a lot of virtual routers with switching. Even with just one, the performance was not so good. Okay, so I'm going to contrast two different techniques of using FPGA reconfiguration and what happens to the network. So let's take a look at a system here which includes two virtual routers, we'll say A and B, that are initially in the network. And the idea would be that virtual router B is going to be replaced from the FPGA with a second network called B prime. Okay, so there's two networks, A and B. Both of them are implemented in the FPGA. There's a desire to shut off the entire FPGA for a period of time, reconfigure the FPGA so it will, instead of just including A and B, it will now include A and B prime. So initially, the throughput here, we can see here we have about 100,000 packets per second when both of these networks are included in the FPGA. When the FPGA is shut off, network A is migrated from hardware, which has high throughput, down here to software, which has low throughput. So for a period of time, A is continuing to forward packets, but at a substantially reduced rate. Okay? So it's doing better than nothing, but it's still taking a long time. Meanwhile, B is shut off, so it's not forwarding anything. 12 seconds later, okay, after all the port remapping and the changes in the physical hardware, we can see here that when A is restored back to the FPGA along with B prime, we can see here that the network regains its full bandwidth. Okay, a couple of points to point out here. The first point is that this particular graph does not show the amount of time necessary to do the place and route and the compile time for the FPGA. So that would be extra. Okay, so that's another even more stronger motivation for partial reconfiguration, in that you could make a bunch of little modules that basically are the same size that could get swapped into the FPGA without having to recompile the entire device, as long as they had the same interfaces on the outside. Additionally, in general, it may not be necessarily possible to know all the different combinations of virtual networks that would be in the FPGA at the same time. Okay, so in general, this approach is fine for initial experimentation, but it's not really a long-term solution. Okay, and we contrast that with the partial FPGA reconfiguration. In this case here, if B is swapped out of the FPGA and replaced by B prime, we can see here that A more or less continues generating sustained throughput. So A doesn't get changed at all. It stays in the FPGA, continues to route its packets happily. And B is shut off after a period of time. There's a much shorter amount of time that the FPGA is down because nothing has to be migrated anywhere. And then B prime is swapped in via the JTAG interface, and it continues along at high speed. Effectively, we get a 20x speed up. It's also scalable in the sense that if I had a lot of virtual networks, I could go ahead and basically just individually swap them in without any problems, okay, based on a schedule. Okay, so the next issue is one of scalability. There's a desire, as I said, to have a lot of virtual networks. In the FPGA, we're limited. Okay, we can only have a total of up to 4 virtual routers in the FPGA. If we're really constrained by partially reconfigurable regions, we can only really have 2. So we did some experiments here with the 4 just to see, to sort of take the best case. So here we can see that if we augment the 4 virtual routers which are implemented in the FPGA, over time what happens is if we augment it with software, we can see eventually the overall throughput, the average throughput, starts to go downward because the software, as we add more virtual routers, they must be in software, and it has a negative effect on the overall throughput of the system, okay, because some things need to be forwarded to the software. In general, the software only does not so good, and we can see that as time goes on, the overall rate more or less stays the same, and then towards the end there's more and more virtual routers. The software has more context switching, and its performance goes down. So what's the takeaway for this particular graph? This particular graph is desirable if there's a lot of virtual networks to have a big FPGA, okay, which it can be partially reconfigured. Okay, what about latency associated with the system? Often in evaluating networks, people look at throughput, but latency is also an important issue. So we evaluated the latency of this particular system here. We can see here that in general, we can see the software only has a much longer latency. You can see this is about 0.1 and that's about 0.7, so about 7 times worse. Over time, the latency here is more or less constant, even as I add virtual routers, because again, the hardware is being used in parallel. But then things quickly get worse as I start adding software routers to the system. Same thing, software in general starts off bad and then gets worse as more routers are added. Another question I sometimes get asked is, why didn't you put, you can get an FPGA that has a hard microprocessor on the FPGA. Why don't you use that for the routing? That's certainly an option. It would make things a lot easier because you don't have to transfer things over the PCI bus. We didn't really have an opportunity to do that, but a longer term, one could consider having just one device that had a hard processor that was doing the software virtual routers, and then the FPGA, which was performing the hardware virtual routing. The Xilinx devices have what's called an ICAP interface, which allows for the device itself to reconfigure portions of its logic. So that might be another option in the longer term for, basically the FPGA could be more or less a self-contained unit, could perform all the routing and could configure itself without a lot of external effort. But we haven't gotten to that point yet. We did a comparison between partial reconfiguration and static reconfiguration, where static in this case is reconfiguring the entire device once again. We looked at using different numbers of ports on the FPGA. So you can think of using all 4 ports for receive and send on the net FPGA board, or you can look at just using 1 port. The key difference here is a question of how often do you have to reconfigure the virtual networks. Okay? So if you don't have to reconfigure that much, it doesn't, it's sort of not pleasant to have to shut the entire FPGA down, but it has less of an impact than if you have to reconfigure frequently. Okay? So if we take a look at this, we can see here that in general, this is the throughput per data plane. We can see here that in general, the partial reconfiguration does the best. Okay? But it's not that much different between shutting the FPGA down, the entire FPGA down for a period of time, if we don't have to reconfigure that often. The gap gets bigger if the reconfiguration takes place frequently. From talking to colleagues, the reconfiguration for the data planes, 180 seconds is pretty fast. I mean, usually these virtual routers stay up for long periods of time. But in general, the partial approach is still a better approach for some of the reasons I said a little bit earlier. Okay, what about the average throughput for the combined hardware-software approach? We don't have a board which has a Vertex 5 in it, but we could make some estimates based on, we were able to compile some of the partially reconfigurable regions into the Vertex 5 and see how fast they are. We can see here that in general, the throughput starts dropping off for the partial reconfiguration versus the static reconfiguration. You can see here that this knee of the curve here, this inflection point, takes place earlier for partial reconfiguration versus the full reconfiguration. And the reason for that is because, as I said, for the partial reconfiguration, it's necessary to, the regions have to be sort of carefully crafted by hand. They have to be a certain size. It uses up a lot more FPGA resources. Okay? So in some cases, it may not necessarily be a good thing to have partial reconfiguration, because then I can't fit as much stuff inside the hardware, because everything needs to be built in a specific way. Okay, so let me say a little bit about power consumption. One of the concerns with FPGAs is power consumption. In general, our power consumption here was pretty good, although in fairness, this is a Vertex 2, which is fairly old technology. I think it's like 130 nanometer. It's pretty old. But in general, most of the power consumption here is dynamic power, as you'd expect with this old technology. Some of the more recent FPGAs, the static power is more important. One of the comments that we got is, instead of dynamically reconfiguring stuff, why don't you just, if you don't need a network anymore, why don't you just cut the clock to save power? We did that. We were able to save about 10% of the power. And you can see up at the top, that's more or less, if we don't use the PCI interface, we can implement 5 virtual routers in a Vertex 2. If we implement the PCI interface but don't support partial reconfig, we get 4. If we support both partial reconfig and the interface, we can support a total of 2 virtual routers in the FPGA. But again, we can support up to 20 in a Vertex 5 device. There's a number of interesting issues associated with this work on the software side. My student is continuing to work on this. And one of them is the algorithms necessary to figure out which networks go in hardware and which networks go in software, and whether the FPGA should be reconfigured if a particular network is created or destroyed. So the student has done a little bit of work on that. There's a question of is it desirable when there's a space available in the FPGA to migrate a network to fill that gap from software to hardware. So the student's done some work on this to take a look at what happens of the upgrades in terms of bandwidth if you go about making the migration. We can see here that in general the amount of time we were able to get improved bandwidth increases if we go about migrating a network from software to hardware. Okay, since the migration path for partial reconfiguration is fairly straightforward. The algorithm takes a look at how much space is available in the FPGA, what the required traffic is, and then it makes a decision based on whether the particular upgrade should take place or not. In some cases, it's not possible to make an upgrade because there's not enough space in the device. So we had a sample of a series of traffic, real traffic in a network, and we were able to find that in about 20% of the time it is possible to make the migration and get an improvement. Okay, so let me finish up. I just want to say a few words about some other things I'm working on at UMass. I have a few slides. You've seen from the presentation here that we were successful in implementing these virtual routers on this Vertex 2 device. Altera recently has provided me with some funding support to migrate the NetFPGA infrastructure to Altera devices. And over the past couple of years, we've migrated pretty much the entire suite of tools from NetFPGA to a Altera DE4. And I have a link on my website which allows faculty and other researchers to go and download the infrastructure. So the packet generator, the reference router, various other infrastructure is available there for free download. The only thing we don't provide is, or we don't have on the website, the Verilog code for the reference router. Stanford doesn't want that on a website because they actually assign their students for a class on how to do that. So I was told that I could have that code and I could give it to people if they requested it, but I can't make it, just download for anybody. So if you're interested, it's on my faculty website, and I'd be happy to send anybody that's interested both the packet generator and the reference router for this board. We target a DE4 board, which is a board that was introduced a couple of years ago. It has a much bigger FPGA on it, a lot more DRAM. It still has 4 1-gig ports. Altera has recently announced, I think within the last couple of days actually, that they have what's called the DE5 board, which has a much bigger Stratix device, Stratix 5 device on it that they're shipping. They have also given my group some money to migrate this experimental platform onto the DE5. Okay? Let me go to the next slide here to show you some of the resource differences. So here's some resource differences between the DE4 and the NetFPGA. So this is the board we're currently using. Here's the DE4. The amount of LUTs is much bigger, and the amount of space taken up by the reference router is a much smaller percentage of the overall device, which gives us much more room to be able to do more virtual data planes and other logic, if necessary, sorting and various other applications in the network. And this is for the DE4. The DE5 is about, I think the Stratix 5 device on the DE5 is about 2 or 3 times bigger than the DE4. There are some limitations. One of the limitations is Altera, at least for the DE4, does not support partial reconfiguration. Okay, so that's a limitation we're dealing with. But for the DE5, I'm not sure if the DE5 has a device that has, I don't believe they do partial reconfiguration either, but I'm not 100% sure about that. So this is a new technology we have. My student who is finishing his PhD is looking at ways of performing computing using these devices, basically embedded MapReduce type algorithms in the virtual network to be able to speed up a system of computers running a asynchronous version of MapReduce.
Are those supposed to be the same design on those 2 different boards?
It's roughly the same design. There's a little bit of difference. You can see that some of the numbers are a little bit different because we had to make some changes in terms of the implementation because in going from Altera to Xilinx. So in this particular case, you'll see that, for example, the memory bits look much less for the NetFPGA board, primarily because the packets were being stored off the chip. For the DE4 implementation that we currently have, we're storing that information on the chip itself. So the numbers look a little bit bigger. But the student is currently working on a DRAM interface to alleviate that problem.
That's probably also where the IOs are that much different.
Yeah, the IO. Well, we have a different. There's a different network interface core that Altera has that we migrated over. We did some experiments with these virtual networking on the DE4 and basically found that we could, again, match the packets per second. We can match, there's no difference between what we could do with the net FPGA and the net FPGA DE4. And that's probably not very surprising since the DE4 is faster and bigger than the net FPGA, but we just wanted to confirm that. So let me wrap up. This project looks at implementing virtual routers on FPGAs. Okay, it's novel in two ways. Okay, when we initially introduced this, we were the first project that had an implementation of multiple different virtual routers on one FPGA. Okay, and we also were the first project that allowed for scalability for both hardware and software routers in the same system, where the hardware is implemented in the FPGA. We think there's a lot of, this has a promising future. There's a lot of future applicability for this because there's a lot of interest in being able to make networks big and small that can basically virtualize hardware at the same time. And I'm sure I'll have a chance to talk to some of you today about that. We were able to demonstrate this in the lab using a net FPGA board. We're currently migrating towards bigger boards to do more experimentation. I think for those of us in the FPGA area, the thing that kind of got me excited was the fact that this really was a great example of why partial reconfiguration is a good thing for FPGAs. And Altera, for many years, kind of resisted doing partial reconfiguration. I think not as a result of this work, I'm sure, but as a result of sort of a broad range of applications using partial reconfiguration, has decided to move into that area as well and provide tool support to be able to deal with them. Okay. One last thing, too, there's a follow-on net FPGA board that the Stanford folks have created in collaboration with Xilinx called the net FPGA 10G. I'm not sure the status. I mean, that board has sort of been in creation for a long time, so I'm not sure of the current status of that board. But there is a competing board, too, with the DE4 board, just to be fair to everyone. OK, thank you very much. Yeah.
Probably going to combine a bunch of different questions. I hit the what a little bit unfairly, but they're all sort of surround scalability. Mm-hmm. So what do you see looking forward to being able to support things like 40 gigabit Ethernet, being able to support lots of more ports, and as in comparison to software-based performance? I mean, it looks like all of this is basically beyond the pale. Based on the numbers that you show here, doing it in some software. But there are some scalability, especially when you get far out, where if you're trying to support lots of different virtual networks, if you just sort of comment.
I think we haven't looked quite that far into the distance. I think there's issues. The place that I would see the issues would be sort of at the interfaces to try to get data onto the FPGA onto the hardware devices, not reach a bottleneck at either the input or the output ports. I feel we didn't spend a whole lot of time optimizing the logic inside the device simply because we could get the performance we needed without having to optimize a lot. I think that if more effort was made, so if there really was a bandwidth limitation, I think additional work could be done to optimize the way the FPGA implementation was created. So I think that is possible, but we haven't really looked at that yet. The student did, one thing I didn't mention in this work, and we have a transaction computer paper that's on my website that describes it. So most of this work is in a TComp paper that the student had accepted a few months ago. There's a whole other area I didn't talk about today, which is how do you implement the forwarding tables, right? So he has this tree-based approach that allows for various levels of lookup for virtual networks, which is very space efficient, right? So as the number of networks increase, there's scalability issues not only in the actual hardware for the router, but also in how to implement some of these things on the device. Yeah.
So often with these partially reconfigurable applications, you get somebody who does it through that, and then somebody comes along and builds essentially a programmable superset.
Right.
Where you say, this is something where what's common is fixed, and what's variable, you've got little options, and you download, just set a couple of registers and go.
Right.
Is that possible to do with what you're doing?
It is possible. So, the question of do you necessarily need to have partial reconfiguration, or can you do sort of a parameter-based setup for configuration? For the types of things we wanted to do for rate limiters and changing, like really changing protocols, you kind of have to reconfigure the hardware for the network. But I think you're right. I mean, in other cases, it may be possible just to have a parameter setting. It's certainly possible. The net FPGA router allows this, and the virtual router allows it too. If you just want to change the forwarding table, there's nothing to reconfigure.
Well, that's kind of going along with what I said. How much variation from virtual router to virtual router are you anticipating? I guess. I mean, how different is the logic going to be in this instance?
I mean, that's a good question. I guess it depends on the application space. So, I would expect if somebody implemented this and let's say was a company selling this, as part of a data center to the outside world. I mean, there may be a large variety of different types of network configurations that might be desirable. If it was sort of within a company and sort of fixed, it may be possible to come up with just a very small set. Yeah.
Way back in the earlier sections of the talk, you mentioned the figure of 12 seconds of total reconfiguration time, mostly because of software.
Right.
How much of that was actually in reconfiguring the FPGA?
It was less. The FPGA is reconfigured in less than a second. It was I think hundreds of milliseconds.
That kind of leads to a second question, and that is, given that there's very little overhead of rate reconfiguration, if you don't have a partially reconfigurable FPGA, why don't you just have two FPGAs?
You could do that too. So
any problems with that?
No, I mean you could have. Well, I mean you'd have to have the physical ports, the networking ports going to both FPGAs. You'd have to have some way of trading off between the two. I mean that's a possibility.
So for a lot of applications, the communication ends up being pretty bursty.
Yes.
And so one way that people get around sort of the scalability issues that you brought up is by temporarily setting up like a circuit switched network.
Right.
How do you see sort of how you might sort of integrate that type of system into what you can bring out?
We haven't really thought about that. I would guess that instead of having partially reconfigurable regions with sort of logical routers, you could have partially reconfigurable regions with data path switches. Although it might be easier, Scott mentioned this, it might be easier for something like that if you just had like a programmable crossbar that you could configure without having to reconfigure the FPGA.
Well, I mean, I guess this only comes up when you start having performance problems.
Yeah.
But I mean, I'm imagining a world where sort of, in order to have really high bandwidth connections, they have to be terribly, terribly wide.
Right.
So you have a ton of data coming in at a given time. Being able to sort of set up that has implications for muxing and that,
right.
and we're even to the point where, in fact, you can't reach the bandwidth limit of the device because sort of one packet is 2 packets, or one packet isn't even the width of the data path that you have coming in, and so they're, yeah. I mean, I'm imagining that this is becoming, especially when the data rate is 40 times what you're currently using, or 100 times. I mean, that happens really easily. So.
I think there is a desire. I'll say for myself. I wish we had a board that had much higher network capacity. So one of the issues in being a researcher is net FPGA is kind of the thing most people are using. I think everybody agrees it's not efficient. The net FPGA 10G has been in planning for 3 years. Until recently, I think there's been a lot of problems, and there were a lot of problems with the physical interface for it for many years. I don't even know if it's available yet. That's kind of what got us interested in DE4. But I would say that as these platforms for research become available, I mean, I would love to do something with 40G and get in there and figure out what the real challenges are on the FPGA side. So, yeah.
Do you have a story for mapping modules to any number of the PR regions you have in your device? Because you're talking about going over to 20 PR regions and wanting to migrate to virtual routers from software, moving it in and out. So.
Right.
We're talking about allocating these as a resource like a cache or something.
Right.
So how would you give a story for that right now?
Yeah, I talked about the allocation algorithm. I think the student. So one of the nice things about the Vertex 5, which is what we didn't actually physically do that on the. We did partially we did completely reconfigure the device and partially reconfigure it for just one router. We didn't do it for 20 routers. So the short answer to that is we primarily just assumed that the partially reconfigurable regions were allocated in a column, a series of columns, and there was software on the computer that would sort of understand what was currently populated and what wasn't, and then would sort of be able to swap things in and out. There probably is an interesting research question in terms of, can you cache these things and get them on the board beforehand and just swap them in as you need them? I think we were using JTAG. I mean, I think an ICAP interface with the processor that's on the board is a much smarter way of doing it. We just didn't do that yet. And I think there's an interesting paper in the allocation algorithm for this that we didn't look at as well. Some of this too is coming up with realistic traces for the traffic so that we can actually show that it makes sense. Yes.
Just a general question: how much buffering do you have for each of the cores? Is that all in the DRAM, or can you fit that on a bigger FPGA? Can you fit all of that on the FPGA? And varying the size of that, what kind of do you see changes in throughput and latency and things like that?
Right. So the experiments we did here were I believe the packets were stored in DRAM, and but it wasn't a limitation in terms of the throughput. The student did another paper where he actually did some. The packets were stored in the SRAM, and the student did another experiment where he moved the packet buffering from SRAM to DRAM and then moved the forwarding tables into SRAM because he needed more space for the forwarding tables. We didn't see that as a limitation on this particular system. Maybe it's because the parallelism in the FPGA was able to route the packets. And the 1 gigabit per second is not, by today's standards, is not tremendously fast. I would guess that as you move to higher speeds, then the memory interface, especially as the packets get bigger, would be a concern. But compared to the Vertex 2, I mean, modern FPGAs have orders of magnitude more on-chip memory.
So given that you're using both DRAM and SRAM, do you think in general cost would be an issue? Because the SRAM chips seem to be very expensive. The FPGA is also...
Yeah.
Do you feel like in future FPGA prices are going to go down and this is going to be something that they can use everywhere? Or?
I think the rule of thumb I often think of for FPGAs is if you wanted the best price point for FPGAs is usually a generation which is one generation old and the middle chip, right? So the high-end chip for any generation is the most expensive. The cheap ones, the real low-end ones, are too small to do anything really useful except for maybe a few embedded, dedicated applications. So the right place to be is sort of like one generation before in the middle. And I think that the prices in that area have consistently been in like the few $100 region for a while. And the price starts, as soon as a new generation comes out, it's like old cars, right? The prices come down pretty dramatically. So I guess the short answer is I think of an FPGA that has suitable resources being similar to a microprocessor, a few $100. But it's not, so it's not thousands of dollars, but it's not $20 either. And all these things are sort of following, I tell this to my students, all these things are sort of following Moore's law, right? So as you get bigger chips, there's more things you want to do with it. So I don't know, that's just my take on it. Yes?
How painful was the transition from the Xilinx to the Altera tools?
So I had a student work on that for about so the tools themselves weren't bad because in my lab we have students that do both Xilinx and Altera. The actual getting the Ethernet core ported took about, I don't know, it took a few months. It took 3-4 months of student time to figure out how to deal with that. We're still working on the DRAM interface. So I mean the student has taken the DRAM interface from the net FPGA and is trying to migrate it, but the technology is different, so you have to sort of look at the flow control and find out why. So just putting a DRAM interface is easy, but then have the packets get backed up and it's not clear like why it's not working and things like that. So it's a work in progress, but the students often will do this for a period of time. It's a 2-year master's, so they'll spend 6 months working on this and then they'll spend 1.5 years using the board to do something useful. I have another project which is funded by NSF, which is looking at network security using FPGAs. So the student's developing monitors in the hardware to actually look at what's happening in the network and that uses the DE4. We're still fairly early in that project. Oh, thank you.